In this video, we are going to study different cases for the behavior of the lamps upon closing and opening different switches. So this is a circuit that's composed of a battery connected into two lamps in two branches, as you can see, and a switch is connected in series to each one of them. So this is K, this is K1, this is K2. Now first we're going to keep the three opened and measure the current passing through each branch. So as you can see here in this case, it is indicating 0 ampere for the main current coming out of the battery. And similarly for the current passing through L1, so 0, no current is passing by, and the current measured while putting the ammeter in series with L2. So this is it. Also 0 ampere, no current passed. Now if we keep the main switch connected in series to the battery opened while we close the switches in series connected to the lamps, also the lamps do not glow, and still the current passing through each one of them is 0. So here, as you saw, it was 0, and similarly now if I connect another ammeter, it's going to be to indicate 0 ampere too. The point is, as well, another evidence for this is that the lamps are not glowing, so there is no current passing by. Why does this happen? Because the battery can't drive the electric current to pass through a circuit unless we have its two terminals connected to each other by a closed pathway. So if we trace the pathway from the positive terminal trying to go to the negative terminal of the battery, we see that this pathway, this one external one, is opened due to the opened switch, or even this one through L1, it's also opened due to the opened switch. So in this case, no current flows through the circuit. Now if K is closed, if the main switch is closed and K2 is closed, there is a pathway, a closed pathway joining the positive terminal of the battery to its negative terminal, as you can see. So a current flows, and the indication is the same in both because simply they are connected in series and there are no branches. So the current won't be distributed. So 0.9 ampere for the main current of the battery, and for the current of L2, it's also gonna be 0.9 ampere because the current comes out here and have only one pathway to follow, so it's not going to be distributed. This is going to be unique. So now if we do close L1 and open the other switch here connected in series, the current is going to flow through L1, as you can see. I'm going to connect the ammeter to measure the intensity. So 0.9 ampere, just like the current that comes out of the battery too in this case. So this is 0.9 ampere also for the other one here. 0.9 ampere. Now the last case is that when we close all the switches, now all pathways are available for the current and all pathways connect the positive terminal of the battery to its negative terminal. So the current passed through all the branches. Now as you can see, the main current increased, it became 1.8 ampere. And let's find the relation between I main, I1 and I2 in this case. So just keep in mind it was 1.8 ampere when all the switches are closed. Now I1 is 0.9 ampere, and let's check I2. It is 0.9 ampere too, so 0.9 plus 0.9 is 1.8 ampere. This was expected because the lamps are connected in parallel, and we know that by law of addition of voltage of current, in parallel grouping, we have I main equals I1 plus I2. Now I have to note here that it happens that I1 equal to I2 only because the two lamps are identical. Otherwise, if they were not identical, for example, if the main current is 1.8, if I main was 1.8 ampere, then if this lamp needs more energy than, if L1 needs more energy than L2, which means that they are different, not identical, then I1 will be greater than I2.